Good morning, all. So, today we'll be discussing about heap and thereby about how to do a sorting using the heap data structure. So, heap is nothing but a tree data structure. It is similar to a tree, but it has got some peculiarities, just like in the case of a binary search tree. So first we'll discuss about what is a heap or what are the various types of heaps available, and then we'll discuss about how you can perform sorting using a heap data structure. So as I said before, a heap is a specialized tree. Okay, so it is very much similar to a tree. It looks like a tree, but it is having some special features, or you can say it is a specialized version or a customized version of a tree data structure. And this tree, the tree that you have customized for becoming a heap, is the customization applied is that it has to satisfy something called a heap property. So what is this heap property? The heap property says that if A is the parent node of B, then the key value of node A should be ordered with respect to the key of node B with the same ordering applied across the heap. So, if you could recollect what we have learned about the binary search tree, we have told that in the case of a binary search tree, the root node is having a particular value. All the elements in its left subtree will be having value less than that of the root node, and all elements in the right subtree will be having a value greater than that of the root node. So that was the BST property. Now talking about the heap property. The heap property says that if you have got two nodes A and B, where A is the parent of B, then if there is an ordering to be applied between A and B, the same ordering should be applied across all the elements or all the pairs of nodes, all the parent-child nodes of the tree. This is heap property. It is not talking that the parent node should be greater than the child node or the parent node should be lesser than the child node. It is specifically saying that there is an ordering and that ordering should be preserved across all the elements of the tree. This is heap property. Now I'll show you an example. So what you see here is a heap. Okay. So as I told before, it is a tree, or to be peculiar, it is a nearly complete binary tree. You cannot claim that it is a complete binary tree. It is a nearly complete binary tree with the following two properties. Structurally, all the leaves will be full, all the levels will be full except in the last level, just like we had in the case of the complete binary tree, and in the last level it was going to be filled from left to right. Okay, now talking about the order property. The order property says in this example, in the example of the tree that is shown below, for any node of x given, its parent should have a value greater than x. But this is not necessarily the same for all the heaps. You have various types of heaps, but the heap that you can see here is having the property that whenever you pick a node, its parent will have a value greater than the node. Okay, so you can see this is the heap. As you can see, it is a complete binary tree. You have maximum number of nodes in all levels except the last level, and in the last level it is arranged from left to right. So the structural property is intact. Now what does the order property say? Whenever you pick a node, whatever node you are picking up, its parent should have a value greater than the node. Okay, so as you can see here you can see a parent 7 which has got two children 5 and 2, and you can see that both the children are having a value lesser than its parent. Similarly, you have another parent 8 here. It has got two children 7 and 4, and you can see both the children of 8 are having a value lesser than that parent. So this is how a order property is satisfied. Okay, so this applies only for this particular heap. You can have a minimum ordering also. Okay, so if this is the case, okay, If this is the case, if the parent is going to have a value greater than its children, then such kind of a heap is called a max heap. Why it is called a max heap is because the maximum valued element of the tree can be found in the root. I repeat, a max heap is that heap where you can see the maximum valued element located as the root of the tree or root of the heap. Such kind of a tree is called a max heap. So it will satisfy this property, which is that parent node should have a value greater than its children. The parent should have a value greater than its children. Suppose if it is the reverse, which means parent is going to have a value lesser than both of its children. Okay, parent is going to have a value lesser than both of its children. If that is the case, then the minimum valued element of the tree will be located in the root node. The minimum valued element of the tree will be located in the new root node, and we call such a heap as a min heap or minimum heap. Okay, so this is about the ordering. So we'll proceed further. And as I said, so this is talking about the minimum heap and maximum heap. Okay, we call minimum heap as min heap and maximum heap as max heap. So in the case of min heap, the minimum valued element will be in the root node. In the case of max heap, the maximum valued element will be in the root node. Similarly, in the case of minimum heap, all the elements, all the parent elements will be having value lesser than their children. Similarly, in the case of a max heap, all the parent nodes will be having value greater than its children. So that is about the minimum heap and maximum heap, the ordering. This is the definition. You can go through it and you can understand for yourself. I'll give you some examples of min heap and max heap. So this is my example. So this is a min heap and this one is a max heap. So as you can see, here you have a root node which is 6 and it has got two children, 7 and 12. This is a complete binary tree. So the 7 and 12 is the children of 6. Okay, and you can see both 7 and 12 are having a value greater than their parent, which is 6. Okay, similarly, when it is applied across the tree, 10 and 15 are the children of 7 and they are having a value greater than 7. Similarly, 17 is the child of 12 and it is having a value greater than 12. So this is applied across the tree, and then you can see the minimum valued element of this group comes in the root, and this is called a min heap. Talking about creating a max heap using the same set of elements, you can see the maximum valued element here was 17 and 17 is the root of this particular tree, root of this heap. You can see there are two children, 15 and 10. You can see that they are arranged in a way that they are arranged to a parent who is having a value greater than them. Similarly, 6 and 10 are children of 15. They are having a value lesser than their parent and they are arranged accordingly. This is applied across the tree and this becomes a max heap, and the other one is a min heap. So this is about the examples for min heap and max heap. So as I said, in the case of max heap, every element will be having an ordering such that they are having a value lesser than their parent. In the case of min heap, they are having a value greater than their parent. Okay. So that is the heap property. Moving further, we have to talk about some interesting features of a heap. First thing is that whether it be a min heap or max heap, the highest or lowest valued element will be always there in the root. Okay, and hence you can pick the highest valued element or the minimum valued element right from the top of the tree, and that's why it is called as a heap. You can relate it with a heap of leaves that you can see in your courtyard. Okay, so the heap of leaves, you can pick the topmost one, and that is the same principle applies here. The highest or the lowest valued element based on whether it is a min heap or max heap, it will be available in the top or the root of the tree, and that is why it is called a heap. Now, I have told that there is an ordering and you can make use of that ordering to sort the elements. So when you talk about a binary search tree, we know that it is sorted because all the elements in the left subtree will be having a value lesser than the root. All the elements in the right subtree will be having a value greater than the root. But this particular ordering or this kind of sorting doesn't apply to a heap. Okay, so in the case of a heap, you can say that it has got an ordering, not a sorting. Okay, a heap is having an ordering, not a sorting. So you can say it is a partially ordered tree. Then, as I said, it is a complete binary tree, and as we all know, a heap with n nodes will always have a height which is equal to big O of log n, which we have already discussed while we were discussing about the binary trees. Now let's move to some examples, and after that we'll see how to insert and delete elements from a tree. So all these, whatever you see here, are all examples of heaps. So you can see in the case of the first tree, it is having a single node. Okay, still it is a heap. In the case of the next one, this is a max heap, sorry, min heap. As you can see, the minimum valued element is in the top of the root. Moving further, this is also another tree. So here you couldn't see any duplication, but here you can see the heap welcomes duplicate entry. I repeat, the heaps welcome duplicate entries. Okay, if it is not violating the rule, if it is not violating the heap property, if you are saying that it should be always greater, you are not supporting greater than or equal to or lesser than or equal to, if you are not supporting it, you cannot claim for duplicate entries. But if you are supporting it as greater than or equal to or less than or equal to, then you can actually have duplicate entries also within the heap. Okay, so all these are some interesting features to talk about heap. Moving further, we'll see how to perform the heap sort. Okay, so before we actually talk about the sorting, in the case of a heap sort, or in the case of a heap, when you apply insertion and deletion, you're actually performing some ordering, some rearrangements, and these rearrangements will actually help you to perform a sorting. Okay, we'll see how that can be done, and but before that we'll know something more about the heap and heap sort. Okay, so as we know, in the case of binary, just like we have in the case of a binary tree, you can have array representation, you can have linked representation, but in the case of a heap, array representation is more advantageous. Talking about the binary tree or the binary search tree, we said that the linked list representation is more advantageous. But talking about a heap, since it is a complete binary tree, we could go for array representation, because you are sure that all the other levels except the last level will be completely full. So the wastage of space will be less, and you can easily pick the data. You can have better access. So taking all these into consideration, you know that the array representation of heap is more advantageous compared to the linked list representation. Okay, then if you have any null entries, or if you have any null entries or vacant entries, it will be towards the end of the array only, and you don't need to preserve all those pointers. You don't need to say who is the parent of whom. That can be applied using the previous rule which we have learned, like if a node is at I, its parent will be in I by 2, its left child will be in 2i, its right child will be in 2i plus 1. We know all that, and you have to just apply it over the machine, and you can find out who is the parent of whom, who is the left child, who is the right child, and everything related to that node. So taking all these into consideration, we have understood that the array representation is more advantageous when you are talking about a heap data structure, and that is why you could apply a sorting based on a heap data structure. Now we'll see how you can insert into a heap. Before you are inserting into a heap, you have to decide whether it is a min heap or a max heap, whether it is a minimum heap or a maximum heap, because whatever to happen after that will be purely based on this decision. Okay, so you have to first ensure whether it is a max heap or a min heap. Okay, so that is your first thing to do. Now whatever happens, so this is a complete binary tree. So as we know, the complete binary tree is going to have elements completely in all the levels except the last level, and in the last level it will be arranged from left to right, that we know. So this indicates that the vacant spaces will be towards the right side of the last level. I repeat, the vacant spaces will be towards the right side of the last level. So always remember, insertion in a heap happens only in the end of the heap. Insertion happens only in the end of the heap, which means you know that the vacant entries will be towards the end of the array, and you have to pick the first vacant space. You will insert it there. First insertion of the node will happen. Okay, you create a new node, you insert it, you will insert the item. Then you will cross check whether the heap property is violated. If it is violated, then you will have to resume the property by rearranging the elements in a particular fashion so that the property is regained. This is how insertion works. Okay, so I repeat once again, always the insertion of a new node will happen in the vacant spaces, which means to the end of the original array, because the vacant spaces will be only at the end of the original array. So you have to identify the first vacant space, you will create a node, you will add the value, and you will perform the insertion. Once the insertion is done, or once the node is added to the heap, then you have to check for whether the heap property is violated. If it is violated, you will have to rearrange the node according to some rules, so that finally the heap will be having this new element without violating the property. You will have to rearrange, you will have to relocate the newly created node so that the heap property is not violated. So this is in general how the insertion happens. So what I do here is that I'll show you an example, and then you will understand how this can be done. So this process of rearranging for resuming or regaining the heap property is called percolation up or shift up. Okay, percolation up or shift up. So I'll talk about this by explaining this particular insertion. So here you can see there was a heap which was having some elements 6, 7, 10, 15, 12 and 17. Okay, 6, 7, 12, 10, 15, 17. This is the array, and it has got one vacant space. Okay, it has got one vacant space, which means you have the freedom to insert one more element into the heap in the last location. If you want to add more levels, then you will have to expand the array. Since this is an array, you have the size restriction also. So you have to be clear about that. Okay, so you have got one vacant space and you have the freedom to add an element. So I am going to add an element which is having a value 5. Okay, so what happens? As I said, the 5 will be inserted at the end of the array. Okay, you are not going to check for the value, you are just inserting it. Okay, so you insert 5 at the end of the array. So you can see here it becomes 6, 7, 12, 10, 15, 7 and 5. Okay, now what happens? This was a min heap. Okay, this was a min heap. The minimum valued element was on the top of the root. Okay, top of the tree. So by inserting this 5, you could see that there is a violation, because what is the rule applied? The node and its parent should be considered, and the parent should have a value lesser than the node, right? So the parent should have a value lesser than the node. So here 5 is inserted as the right child of 12, and you can see 12 is having a value greater than 5, which means you have to exchange between 12 and 5. So you can see here 12 and 5 are interchanged. Can you see? So 12 takes the position of 5 and 5 takes the position of 12, so that the array becomes 6, 7, 5, 10, 15, 17 and 12. So now what happens? The tree becomes 6, 7, 5, 10, 15, 17 and 12. Okay, so 5 is here. Now you compare 5 with its parent. So what was the parent of 5? It was 6, right? It was 6. So what happens? Again the heap property is violated. So what you have to do? You have to shift 5 again. So 5 and 6 will be replaced. Okay. So 5 and 6 will be replaced. They will be interchanged. So what happens? 5 takes the position of 6. 6 takes the position of 5. And you can see 5 takes the position of 6. 6 takes the position of 5. The newly created heap, after resuming or regaining back the heap property, will be having its root as 5. So you can see it becomes 5, 7, 6, 10, 15, 17 and 12. This is how insertion happens in a heap. Okay, this is how insertion happens in a heap. So this was in the case of a minimum heap. In the case of a maximum heap, I have another example for you. So here you can see this is a max heap. The maximum valued element is available in the root. Okay, I'm going to add a new element. Okay, so I'm going to insert 15. X is equal to 15. So what happens? You know it can be inserted only in the end of the array. So you know it will be inserted as the left child of 8. Okay, because that was the first vacancy. So a 15 will be inserted as the left child of 8. You compare, so insertion is done. What you do is that you compare between 8 and 15. You compare between 8 and 15. You understand that this is a max heap and you have to perform some arrangements because the heap property is violated. So what happens? 15 takes the position of 8, 8 takes the position of 15, and you can see that in this figure. Okay, 15 takes the position of 8 and 8 takes the position of 15. So they are kind of swapped between themselves. Now this problem gets solved in this level. But what happens about this level? The next level, you have to again cross check. You understand that the parent of 15 is now 11, which is having a value lesser than 15, which means the heap property of max heap is again violated. You have to regain it by swapping them. So what happens? 15 and 11 will be swapped between themselves. 15 takes the position of 11 and 11 takes the position of 15, thus creating this particular heap and regaining the heap property. So this is how insertion happens. Okay, this is not just in the case of elements having or tree or heaps having just 2 or 3 vacancies. If you are going to build a new heap from the scratch given with a sequence of elements, you can do the same according to this particular principle. The first element of the array will be taken as such. You don't have any violation. But when you are inserting the second element, from this element, the second element being inserted, from that point you will have to check for the heap property, whether it is violated, whether it is not violated. If it is not violated, then it is well and good. You can keep the insertion as such. If you have a violation, then you have to swap between them, node and its parent. So this is about insertion. So this is an algorithm for inserting in a max heap. Okay, when you're talking about a min heap, you have to just make some small changes. Okay, so I'm talking about the max heap here. So you have an item, you have to insert something. So you have that item, which is the data to be inserted. And you also know what is the number of nodes, because this is an array representation. You have size limitations. Okay, and the data structure applied is an array which is having a size according to that is being specified by the user. Now, talking about this, what you're going to do is that you are having a value which is n, the number of nodes. Then if you are checking whether it is greater than the size, then you have to say that it is not possible to insert. The heap is already saturated. This is in the case only when you are using the array. Okay, you are using the array, and that is why you have got size restriction. Now talking about the other thing, okay, if it is not the case, then what you have to do, you have to, so n is the current number of nodes, you have to increase them by 1, okay, because you are going to have a new member to the family. So what you're going to do, you are just taking the number as n is equal to n plus 1, and at that position indicated by a of n, you have to paste the item. Okay, this is because the array index starts from 1. Okay, you had 5 elements, the array was having a size 10. You have the positions from 6, 7, 8 and 9 and 10 as vacant. Now you're going to insert the 6th element. Okay, n is currently 5, you upgrade n as 6, then at the position a of 6 you are going to insert the new element. Okay, so insertion happens. After the insertion happens, now I is equal to n, because you have inserted it that at that position. So you have the node at I. Now you have to check for its parent. So since it is an array implementation, you know that the parent of that particular node is available at I by 2. So you find I by 2 and you can know that it is available in P. Okay. Now what you have to do, you have to check whether P is greater than 0. Okay. Which means it is part of the array. Okay. It is available because the array index is starting from 1 to n. So you have to ensure that whatever you have got as P by 2 is part of the array. If you are getting it as a value 0, that means it is a root. Okay, you are inserting the first element, it is the root, so you cannot go for finding the parent of it. Parent doesn't exist. So that is this case. P greater than 0, p less than 0 implies, or p equal to 0 implies the node which was just inserted was a uh, was a what I say, it was a root node. Okay, then you have to ensure, since this is a max heap, okay, since this is a max heap, you have to ensure that the parent is having a value greater than the child. Okay, so what you do, you compare between a of p and a of I, and if you understand that a of p is having a value lesser than a of I, you can take it as even lesser than or equal to. Okay, so a of p is lesser than or equal to a of I, what you have to do, you have to swap. Okay, so you just sorry, a of p is less than a of I, you don't have to take equal to, because equal to is acceptable. Okay, so if a of p is less than a of I, what you have to do, you have to just swap. So you swap between a of I and a of p. So the element at a of p takes the position of a of I, and a of I is swapped with a of p, and that is done. Now what you have to do, you have to uh, get that particular index. Okay, so you get the index, what is the newly created index, and that index is marked as t. Okay, now what you have to do, now you have to compare with this particular element and the other parent. Okay, the next level parent. So that is why you take it as t is equal to p, and p is upgraded as p by 2. Okay, just like in this example, we first compared with 15 and 8, then we compared with 15 and 11. Okay, so that is why p is upgraded as p is equal to p by 2. Then this process repeats until you maintain the heap property. So this is the algorithm for heap sort, insertion into a heap sort. Okay, so just like insertion, deletion also has got some particular features. Okay, we have learned about 3 cases while you are deleting from a binary search tree, but here we have to talk about some rules that are going to affect the deletion inside a heap. Okay, which is again a complete binary tree. Now talking about deletion, in the case of a minimum heap, the minimum valued element will be at the root. And for your information, in the case of in the case of a heap, deletion always happens from the root. Okay, I repeat, in the case of a heap, you always delete the first element. In the case of a heap, you always delete the first element or the root element. So when you delete a root element, what happens is you replace that element with the last element of the array. Okay, so whenever you are going to delete the root, it is replaced with the last element of the array. Okay, so you will replace it with the last element, then you actually check for whether the heap property is violated. If the heap property is violated, then you will have to interchange between the node, between the root node and any one of its 2 children. That will be decided based on what is the property of the heap, and then this will be done until you reach a point where the heap property is satisfied. Okay, this process of shifting the element down towards the leaf level is called shifting down or percolation down. Okay, so I'll show you an example and you will have a better understanding about this. So just like in the case of minimum heap, in the case of maximum heap also, you delete the root node, you take the last node as the root node, then you check whether the heap property is violated, which means the parent is having a value lesser than the child. Then you will have to interchange accordingly, you have to shift down and finally regain the heap property. So I'll first discuss about the algorithm, then I'll discuss about the solution, the example. So as I said, this is about the max heap. Just like we had insertion in the max heap, here you have a heap which is having some nodes, then you have to delete something. Okay, so deletion always happens in the root node. Now if n is equal to 0, which means the heap is empty, then you cannot perform deletion. You will have to say that such a tree does not exist, or it is empty. Then you can come out of the program. Now if it is not, what you have to do, the item to be deleted is the first node of the array, which means the root node of the heap. Now you have to take it as item, then you have to replace it with the last element. And what is the last element? It is available in a of n. So a of 1 is replaced, as you can see in line number 6. A of 1 is replaced, you have stored the value in item and it is being, that position is replaced with A of n. Okay, and you decrement n by 1. Okay, so up to that everything is very good. So you have done that. Now you have to check whether the heap property is violated. How will you know whether the heap property is violated? For that you have to identify what is the left child, what is the right child, so and so. So you have set something called a flag. Okay, you have set something called a flag, and I is having a value less than n, I is initially equal to 1. Now what you do, you have the element, okay, you have this particular element, you have to compare with its left child and right child to know whether the heap property is violated, right? So you have the element at I, you have its left child at 2i and right child at 2i plus 1. So you identify those elements. Now what you have to do, you have to check whether left child is less than or equal to n. Okay, if left child is less than or equal to n, then what does that mean? Left child is less than or equal to n means you, whatever you got as the value is having a value less than or equal to n, means you have it inside the array. It is not a leaf node. Okay, the node at position I is not a leaf node. If it was a leaf node, you will have a value for 2 into I as out of the bound. Okay, it will be having a value greater than n. If it is not, then you will mark that particular value of value at the left child index as x. Okay, x is the value that is being available in A of L child. Else x will be having a value in negative infinity. Similarly, you check for what is 2 into I plus 1. You get something, you call it as R child. You check whether it is having a value less than or equal to n, which means it is inside the array. Okay, it is inside the array bounds. If it is, then you will store that particular value as y. Else, you will take it as minus infinity itself. Now, you have to check. This is a max heap. Okay, this is a max heap. So you have to check whether a of I is greater than x and A of I is greater than y, which means the parent is having a value greater than both of its children. If that is the case, you can say flag is equal to true, which means the heap property is maintained. Okay. Else what you have to do, you will have to perform a swap. So you have to check whether x is greater than y and A of I is less than x. Okay, x is greater than y and A of I is less than x, which means x is having, the left child is having a value greater than the parent. Okay, x child is having a value greater than the parent, then you have to swap between the left child and the parent. And in the case of the opposite, this will happen, I will be updated as the left child value and this process will go on. Next, if it was the opposite, which means I is having, A of I is having a value less than the right child of that particular I, then you will have to swap between A of I and its right child, and this process, the R child, I will be updated with the R child value. This process continues until a position where you can find that the flag is equal to true, which means A of I is having a value greater than both of its children. So this is about deletion. Now we'll have an example. Yes, so this is my example. Okay, so here I have got some values. Okay, so I have got some values. So what happens is, there was an element here, there was the root element, the root element is taken out. This was a max heap. Okay, this was a max heap, there was a root element. Take the root element as 9. Okay, so 9 is deleted. What happens, the last element of the array was 4 and 4 is replacing 9. So 4 becomes the root. Now what you have to do, you have to identify x is equal to 5 and y is equal to 8. Now you have to compare between A of I and you have to compare between A of I, A of L child, A of I, A of right child. Now you have to identify which one of them is greater, since this is a max heap. What you have to do, so L child is there, right child is there, you have to compare. Then what you have to do, you have to swap. So here you can see 8 takes the position, 4 becomes the right child of 8. So that heap property is satisfied. Okay, so this is about deletion. You can have your own example, and I will recommend you to go for this particular problem. Okay, this problem, and try deleting. So this is your main heap. Okay, we have discussed about max heap, so you have a main heap here. Just try and find out what happens when 5 is deleted. So 5 is the root node, it gets deleted. So 5 is deleted, 12 takes the position of 5. What happens rest? That is your work along with this problem. Okay, so if you have any doubts, you can contact me. Thank you.